together. Now let's talk a little bit about different parts of the brain. Now, there's some things you don't actually need your brain to do. The study of what you don't need your brain to do has often drawn upon this weird methodology where this was actually done in France a lot, where they would decapitate people. And when after they decapitated people, psychologists would rush to the body of the headless person and sort of just test out reflexes and stuff like that. It's kind of gruesome. But we know there are some things you don't need your brain for. You don't need your brain for newborn sucking, limb flexation and withdrawal from pain. Your limb will pull back even if your head is gone. Erection of the penis can be done without a brain. Vomiting, also done without a brain. Here, I need a volunteer. Very simple. This will not involve any of the above. Could you stand up? Just, okay. This is a new shirt, so I want to stay away. No, this is, if you hold out your hand, and one hand flat, excellent, excellent. That's the textbook, 5th edition. Now, perfect. What you'll notice is, thank you very much. What you'll notice is this hit and this hand went back up. This is something automatic, instinctive, and does not require your brain. So your brain isn't needed for everything. What does your brain do? Well, some things that your brain does involve very low-level internal structures. And these are called subcortical structures because they're below the cortex. They're underneath the cortex. So for instance, what we have here is a diagram of the brain. The way to read this diagram is, it's as if it were my brain, I'm facing this way. My head gets cut in half, down here. And then you could see the brain. So this is the front over here, that's the back. Some key parts are illustrated here. The medulla, for instance, is responsible for heart rate and respiration. It's very deep within the brain, and if it gets damaged, you're likely to die. The cerebellum is responsible for body balance and muscular coordination. And to give you, again, a feeling for the complexity of these systems, the cerebellum contains approximately 30 billion neurons. The hypothalamus is responsible here for feeding, hunger, thirst, and to some extent, sleep. And here's the same brain parts in close-up. Now, all of these parts of the brains are essential, and many of them are implicated in interesting psychological processes, but where the action is the cortex. Isn't this beautiful? The cortex is the outer layer, and the outer layer is all crumpled up. You ever wonder why your brain looks wrinkled? That's because it's all crumpled. If you took out somebody's cortex and flattened it out, it would be about 2 feet square, sort of like a nice, like a rug. And the cortex is where all the neat stuff takes place. Fish don't have any of it, so no offense to fish, but I think that's fish don't have much of a mental life. Reptiles and birds have a little bit of it, and primates have a lot, and humans have a real lot. 80% of the volume of our brain is cortex. And the cortex can be broken up into different parts, or lobes. There is and again, this is facing in profile forward. There is the frontal lobe, easy to remember, this part in front. The parietal lobe, the occipital lobe, and the temporal lobe. And one theme we're going to return to is, this is half the brain. This is, in fact, the left half of the brain. On the other half, the right half, everything's duplicated with some slight and subtle differences. What's really weird, one really weird finding about these lobes is that they include topological maps. They include maps of your body. Here's a cartoon which actually illustrates a classic experiment by some physiologists who, for some reason, had a dog's brain opened up and started shocking different parts of the brain. You could do brain surgery while fully conscious because the brain itself has no sense organs to it. And it turns out that the dog, when they zap part of its brain, its leg would kick up. And it took Dr. Penfield at McGill University to do the same thing with people. So they were doing some brain surgery. He had a little electrical thing just on. I don't know how he got to do this. He started zapping it, and boom, the person's parts of their body would move. More than that, when he zapped other parts of the brain, people would claim to see colors. And he zapped other parts of the brain, people would claim to hear sounds. And other parts of the brain, people would claim to experience touch. And through his research and other research, it was found that there are maps in the brain of the body. There is a map in the motor part of the brain, the motor cortex, of the sort up on the left, and the sensory cortex of the sort that you could see on the right. And you could tell what's what by opening up the brain and shocking different parts, and those parts will correspond to the parts of the body shown in the diagram there. Now, two things to notice about these maps. The first is they're topographical. And what this means is that if two parts are close together on the body, they'll be close together on the brain. So your tongue is closer to your jaw than it is to your hip in the body. So too in both the motor cortex and the somatosensory cortex. Also, you'll notice that the size of the body part represented in the brain does not correspond to the size of the body part in the real world. Rather, what determines the size in the brain is the extent to which either they have motor command over it or sensory control. So there's a whole lot of sensory organs, for instance, focused along your tongue, and that's why that's so big, and an enormous amount on your face. But your shoulder doesn't even make it on there, because although your shoulder might be bigger than your tongue, there's not much going on. In fact, if you draw a diagram of a person, what their body is corresponding to the amount of somatosensory cortex, you get something like that. That's your sensory body. Now, so you have these maps in your head. But the thing to realize is, and these maps are part of your cortex, but the things to realize is that's an important part of what goes on in your brain. But less than 1/4 of the cortex contains these maps or projection areas. The rest is involved in language and reasoning and moral thought and so on. And in fact, the proportion, as you go from rat, cat, monkey, humans, less and less of it is devoted to projection areas and more to other things. So, how do we figure out what the other parts of the brain do? Well, there's all sorts of methods. Typically, these are recent imaging methods like CAT scan and PET scan and fMRI, which, as I said before, show parts of your brain at work. If you want to know which part of your brain is responsible for language, you could put somebody into a scanner and have them exposed to language or do a linguistic task or talk or something, and then see what parts of their brain are active. Another way to explore what the brain does is to consider what happens to people when very bad things happen to their brain. And these bad things could happen through lesions, through tumors, through strokes, through injury. For the most part, neuropsychologists don't like helmet laws. Neuropsychologists love when motorcyclists drive without helmets, because through their horrible accidents, we gain great insights into how the brain works. And the logic is, if you find somebody, crudely, if you find somebody with damage to this part of the brain, right here, and that person can't recognize faces, for instance, there's some reason to believe that this part of the brain is related to face recognition. And so through the study of brain damage and the study of, we can gain some understanding of what different parts of the brain do. And so people study brain damage that implicates motor control, such as apraxia. And what's interesting about apraxia is it's not paralysis. Somebody with apraxia can move do simple movements just fine, but they can't coordinate their movements. They can't do something like wave goodbye or light a cigarette. There's agnosia. And agnosia is a disorder which isn't blindness, because the person could still see perfectly well. Their eyes are intact. But rather, what happens in agnosia is they lose the ability to recognize certain things. Sometimes this is described as psychic blindness. And so they may get visual agnosia and lose the ability to recognize objects. They may get prosopagnosia and lose the ability to recognize faces. There are disorders of sensory neglect, some famous disorders. Again, it's not paralysis, it's not blindness, but due to certain parts of damaged parts of your brain, you might lose, for instance, the idea that there's a left side of your body or a left side of the world. And these cases are so interesting, I want to devote some chunk to a class in the next few weeks to discussing them. There are disorders of language, like aphasia. The classic case was discovered by Paul Broca in 1861, a patient who had damage to part of his brain and can only say one word, tan. And the person would say, tan, 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 tan. And everything else was gone. There's other disorders of language, such as receptive aphasia, where the person could speak very fluently, but the words don't make any sense, and they can't understand anybody else. Other disorders that we'll discuss later on include acquired psychopathy, where damage to parts of your brain, particularly related to the frontal lobes, rob you of the ability to tell right from wrong.